If I tell you that a coffee mug is similar to a donut, will you be surprised? Of course, most people will be surprised unless you are a mathematician. To understand how a coffee mug is similar to a donut, we need to have a certain amount of concept of topology. Topology is a branch of mathematics where you study geometrical properties of objects under various kinds of deformations, such as stretching, compressing, and things like that. Under this type of deformations, the object's geometrical property will remain unchanged. So this type of behavior or characterization can be studied in the field of topology. Why is it so important? In artificial intelligence, especially in computer vision, it has direct applications. There are certain algorithms which employ manifold learning technique where the higher dimensional images are converted into lower dimensional representations, keeping certain properties of the higher dimensional images same in this lower dimensional representation. So this involves that knowledge of topology. If you have a good grasp on the topology and topological spaces, I'm sure you will be good at computer vision and your project will be very smooth. So without further ado, let's go back to the definition of topology. We will try to define topology in terms of axiomatic set theory. The beauty of mathematics is that one concept can be explained or can be conveyed by using different perspectives, such as using algebraic equations, polynomials, or even differential calculus and geometry, or even by using this logical reasoning of set theory. We will try to define topology in terms of set theory. Let's say M is a set and N is a set of subsets of the power set of M. So what is a power set? If you recall the basic definition of power set, say M is equal to 1, 2, 3. So power set is basically the collection of all possible subsets of M. Let me delete it. So this is M. So what would be all the possible combinations of this set M? Let's try to pick one by one. So let's try to pick 1 first, and then 2, and then 3. So I'm making all the possible combinations. Now let's take a pair of them, 1 and 2, and then 1 and 3, and then 2 and 3. And now let's take 3 of them together. So if I take 3 of them together, then I have 1, 2, 3, all of them. And now let's not take any of them at all. So any of them not present means nothing is present, which is denoted by the symbol phi. That means empty set. So P is the collection of all possible combinations of the subsets of M. So in order to find out how many elements can be present in the power set of any set, that can be counted by a formula called 2 to the power n, where n is the number of elements. So the number of elements of n is actually 3. So the power set will contain 2 to the power 3 or 8 elements. So let's count how many elements are there in the power set at Pm. 1, 2, 3, 4, 5, 6, 7, 8. So our formula suggests the perfect thing, 8 elements in the power set of M. Now let's go back to the original definition of topology. So we have two sets. M is a set and N is a set of the subsets of the power set of M. Now N can be called topology on N. So N can be called topology. N is a topology on M if it satisfies 3 axioms. So axioms are the mathematical conditions in very strict and rigorous sense, basically. So 3 axioms must be satisfied in order to call n is a topology on M, number one, the empty set phi must belong to n. So this symbol means belongs to. So phi should be a member of n, and M must be a member of n as well. This is the first axiom. So the second axiom should be, if I take two elements of n, say the two elements are a and b, if I take two elements from n which belong to n, then if I take the intersection of these two elements, the resultant member should be also present in n. So if I take any two elements of n, if I take the intersection of those two elements, then the resultant element should be also present in n. This is the second axiom. The third axiom states, it's kind of similar to the second one. If I take a number of elements, say A alpha, so I have A, B, C, D, E, F, G, a number of elements, for example. So I'm just shortening it by using alpha, which I have from n. And if I take the union of all the elements that I have taken from n, that is A alpha, that is basically alpha, then this resultant member should be also present in n. All right? If I can satisfy these three axioms, then n is a topology of M. Now let's give an example. It's better to understand from an example point of view. Let's say M is equal to 1, 2, 3. And n is equal to 1, 2, 1 and 2, 1, 2 and 3, and then 5. Now the question is n a topology of M? Is n a topology? We have to figure it out. Let's check the axioms one by one. All right. The first axiom states that phi set must be present in n and M must be present in n. Let's check this condition. Is phi set inside n? Yes, phi set is inside n. Is M inside n, or M is a member of n or not? So M is 1, 2, 3. Is this present in n? Yes, this is present in n. So our first axiom, which states that phi is a member of n, it is satisfied. It also states that M should be a member of n. It is also satisfied. So our first axiom is totally satisfied. Now let's come back to the second axiom, which states that if I take two elements from n, then if I take the intersection, this member, the resultant member, should be also present in n. Let's give an example. Take any two of these members from n. Let's take any of them, any two of them. Let's take 1, 2, 3, and 5. And take the intersection 1, 2, 3, and phi. If I take the intersection, what would be the result? The result is phi, because there is nothing common between these two elements. So is phi a member of n? Yes, it is a member of n. So our second axiom is correct. I can verify for the other elements. If I take 1 and 2, then 1, 2, and 1 intersection gives the result of 1. So 1 is a member of n. So our second axiom is also satisfied for these two elements. You can check for all of them and you will find this thing. Now coming back to the third axiom, which states that if I take a collection of elements from n and take the union, then the resultant should be also present in n. Now let's take a collection of elements from n. Let's take 1, 1 and 2, and 5. Let's take 3 of them, 1, 1 and 2, and then 5. And if I take the union together, then I can see the resultant member 1 and 2 is a member of n. So that means our third axiom is also satisfied. So you can check for the other elements as well. So since we have all the axioms being satisfied, I can say that N is a topology of M. So N is a topology of M. All right. Now, coming back to the topological space, the definition for topological space. Since a few moments ago, we just saw that N is a topology of M, right? M was a set and N was another set, and we proved that N satisfied three axioms, and then we call that N is a topology of M. Then the topological space, the definition is that M and N, this set is basically a set that forms a space that is called topological space. All right. So this is the definition of topological space. It's basically the set of these two sets. They are interrelated by these three axioms together, and they form a space called topological space. Now, the first question of this very video was that a coffee mug is similar to a donut or not. So coming back to this discussion, this line of topic is basically interesting. A coffee mug is basically very weird from donut. If only common thing is this ring, right? A donut has a complete ring, and a coffee mug is a kind of like partial ring. Now, how could these two 3D objects are similar? If you let's think in this way. Let's say you have a donut which is very flexible. Say it's a very soft material. You can deform it as you want, and it will not break. All right. So you give enough pressure. You give enough pressure here and here, and you try to mold it by giving some gentle pressure, and it will again, bulge out, and then certain amount of pressure will create a shape like this. Say this shape becomes like this. All right. Now it becomes like this, and then you have this ring part. And then you can also truncate the corners or make it round, whatever you want. It doesn't matter. The cup is also rectangular, so it is same actually. Anyway, so basically by using some pressure and certain force, you can turn out this flexible donut into a coffee mug. The interesting fact is that mathematically they are equivalent. In terms of topological space, they're called homeomorphic. Homeomorphic are those objects. Homeomorphic are those objects which are basically can be obtained from one another without cutting it, without gluing it, or without making any discontinuity. So you just pressed it here, this flexible part, and it just came out to be a cup like that. And the mathematical properties of these homeomorphic objects are same. So if you have a complicated geometry like this coffee mug, you can certainly study the geometrical properties of these complicated objects in terms of simpler objects like a ring, this donut, or mathematically we call it torus. All right, it's basically same. Donut and torus are basically same. Anyway, so these homeomorphic objects are basically same. They have common geometrical properties. If I give you a sphere and a cube, can you tell whether they are homeomorphic or not? What do you think? Can you make a sphere from a cube? Yes, you can. You can. If you give enough pressure, say these objects are flexible for the convenience of the discussion. Let's assume these objects are completely flexible. You can give pressure and they can deform. I already told in the very beginning of this video that topology is the study on the various kinds of deformations, twisting and compressing, stretching, things like that. You cannot cut it, but you can definitely compress it, stretch it, twist it. Coming back to this discussion, you can definitely decompress these corners of these cubes and make it round and round in such a way. And you can also give some pressure in the middle so that it turns up to be certainly like that in some shape. And you can also compress a little bit from the top and bottom corners. That turns out to be a perfect sphere at some point. So definitely a cube and a sphere, they are homeomorphic. Right? If you have complicated geometry where, for example, you have a geometry like this surface doesn't have any regular shape, for example, this is a 3D object and you don't have any regular shape, you don't know whether this object and this object, they are homeomorphic or not. How do you compare these two objects? So this problem is very interesting. In order to solve this kind of complicated geometry, you can use meshing. So meshing is a technique. It's a technique where we divide the 3D space into basic polyhedron like tetrahedra. So tetrahedra is the 3D counterpart of the triangle. You can basically represent or divide or discretize this 3D space into various tetrahedrons. All right. So tetrahedras, basically you can convert this 3D space into various tetrahedra, and you can also do that for this. So if you divide this entire space with this meshing techniques and you count the number of vertices, so vertices are these end corner points. These are the vertices. If you count the number of vertices, and then if you count the number of edges, these are the edges, and subtract it from the vertices. And if you add the faces are the planes, these 2D planes. All right, so these are the faces, 1, 2. On the other sides are basically 4. So if you add them together, so this number is called Euler characteristics. Euler was a mathematician. Euler characteristics. Now, if you do the same thing for this object, and if their Euler characteristics match together, then, they are equal, then you can call these two objects are homeomorphic. So that is how we characterize the complicated three-dimensional objects which do not have any regular shape like a cube or a sphere or a torus. This kind of applications are very useful in spherical convolutional neural network, where we try to detect objects from three-dimensional pictures. It has direct application in computer vision. So this was a very introductory lecture of topology and topological space, kind of like a review for the experts, and very easy to follow for the very fresh starters. So thank you very much for watching this lesson.